All right, hey, everybody. We can go ahead and get started today. Like always, everyone who called in, thanks. Glad you're here. Everyone who isn't here, we're recording this, so hopefully you're watching it a little later on. We're going to pick up where we left off last time. We were talking about filters. Before we kind of keep going with that, I guess just kind of some general announcement type stuff. Project one is due today. So I've been answering a lot of questions on the Discord and we've got some email questions. It seems like everyone's kind of good. Looks like no one's waiting on an answer from me on anything. So I hope that's going well for everybody. Seems like it's fine, at least at this point. I would hope so. Yeah, just get it in by the end of today. If for some reason you don't think you're going to get it in by the end of today, let me know and we can kind of talk about it and work something out. If for some reason you don't think it'll be done. And I think, according to the calendar, the next assignment is going to be given out on Thursday, either Thursday or next Tuesday. Next Tuesday is when we'll go over assignment one. I'll grade everything this week, and then we'll go over grades and stuff on Tuesday. So just kind of give me the rest of the week to look through everyone's assignments. And then I'll put out project two, which will move into edge detection and filtering and all those kind of fun topics. So unless there are any questions about the homework or getting it in today, which seems like there are not. So I will go ahead and share my screen and we can pick up where we left off last time. All right, so kind of get everything moved around here so I can see the chat, Discord, in case there are any questions. And so today we're going to be talking about edge detection. Last week, we were talking about filters and kind of the pre-processing part of computer vision and CV, where we were working through the idea that different CV algorithms see things differently and care about different information, which is why we kind of talked about color spaces for a couple classes to sort of talk about, what color space do humans kind of operate in, what color space do computers like to operate in, and in particular how we do segmentation and edge detection using kind of the hue saturation spaces. And we do that because when we are looking for edges, we're basically looking for big changes in intensity, either getting more intense or getting less intense. And so to kind of prepare for that, we talked about high pass and low pass filters, which were just different kinds of convolutional kernels that average out or smooth out or sharpen kind of each pixel's value as a function of its intensity and the intensity of everybody around it. So we looked at those two 3x3 convolutional kernels and just sort of like how we had, hue saturation, value, lightness, and intensity. Each of our filters kind of worked in a similar fashion where we had, our smoothing filter that averaged everything out, and we had our high pass filter, which only kept the high stuff, which was kind of like, our max intensity, and our average was our sort of relative max, and then our blurring or our low pass was sort of the lowest. So those were our filters we talked about. So now today we're going to do edge detection, and it's kind of included in the unit on filters because edge detection is like a filter. It works the same way filters do with convolutional kernels. And the idea is, you're using it to filter out edges so that you then work with the edge image to kind of do your computer vision. So what we're going to talk about, our high pass and low pass filters in our pre-processing, and then, what is edge detection? Excuse me, and what do we do with it? So, like I was saying a minute ago, we need filters because different CV algorithms need to see different things. We talked a fair bit about why geometry matters more than color if we want to do sort of an initial segmentation. And then once we have filtered out the edges and we have kind of segmented things based off geometry, classification and anomaly detection and all these sorts of things can then, kind of jump in and do their job using more information like color and texture and things like that. So our high pass and low pass we talked about. We have the sum, the average, and the weighted average are kind of our three options with the high pass, low pass, and Gaussian. And so all of that stuff gets wrapped up into edge detection because we think about edges as a place in the image. Excuse me. So an edge is a boundary where there's a big change in pixel intensity. So anywhere there's a really big change in kind of what the image is, what's inside the image, that's going to kind of go in and label that as an edge. And that's sort of what we saw last time was if we tried to do edge detection on low pass and high pass filtered images, we got, some pretty interesting results where the easier it was for us as people to find an edge, kind of made it harder for the computer to find an edge. Oh, man, it's almost Tuesday to every Tuesday. And so something that looked like a really big jump to us, the computer kind of found everything. So when we tried to do edge detection on a high pass image, it finds every change. So we got incredibly messy images, line images. And if we did it on a low pass, it didn't look as good to a person, but the changes were more pronounced in that only the big changes got caught, right? So versus a high pass where it sees sort of every change as an edge with a low pass because everything's blurred out and only sees the really big changes as an edge. And essentially to detect edges, we're using a gradient function to figure out how much the intensity changes from one pixel to the next. So how it works is the first thing we're going to do is come up with some sort of parameters to tell it what kind of intensity change or amount or shape or direction, whatever, that's going to kind of tell it if it's within these bounds, then it's an edge. And then we apply this gradient function to find out where we see those changes in intensity that we've sort of said will count as an edge. And so every edge detection algorithm is pretty much, I say every, there's always exceptions, but overall, any edge detection algorithm is going to be some variation of the Sobel operator. And kind of as it is out of the box when we pull it out of, say, OpenCV, this is kind of what it gives us is the base case, is a Sobel operator. And, kind of as sort of the basic case, you don't have to do any sort of filtering to use it. You don't have to do any pre-processing. It's sort of, just your straight out the gate edge detection, algorithm. And then you kind of build on that to do better edge detection. But the way it works is it's two consecutive convolutional kernels. So we apply one kernel to find horizontal edges, and we apply one kernel to find vertical edges. So it's basically two filters, two convolutional kernels. One of them filters out all of the things that aren't on a horizontal line, and one of them filters out all the things that aren't on a vertical line. And that's how we get kind of our GX and GY. And then based off of that, we create our gradient images. And so that's sort of what we talked about last time, is looking at the change of the change is what the gradient is. So we're looking for, is there a big change in intensity, and is there a big change in the way the intensity is changing? So we've got these gradient images, and then we calculate magnitude for them using our IX and IY, and then we apply some threshold to that gradient image. So I'll kind of walk through each of these steps in a little more detail so they can kind of make a little more sense. But conceptually, the Sobel operator is just, a convolutional kernel to look for vertical edges and a convolutional kernel to look for horizontal images, and then differencing to find the gradient, and then finding edges based off of that gradient's magnitude. So this is our Sobel operator. Again, this is straight out of the box. So what you've got is a horizontal kernel. It looks at, everything to the left and then everything to the right. And it gives a lot less weight to what's on this side and a lot more weight to what's on this side. And so as that moves across, going from right to left, right, it's going to basically continuously put more information on the sort of next row it sees and a lot less on the previous row. So, if everything kind of looks the same as you're going right to left, you're not really going to change a lot. But if there's a big jump to a much more intense line or area of the image, then it's going to get amplified by, a factor of 1 or 2, as you can see from the kernel, whereas the prior information is getting a lot less emphasized. So that's going to kind of, as you march, right to left, anytime there's a big change in intensity, it's going to show up pretty strongly. And the same for any time there's a big dip in intensity kind of as you move across. That will sort of stand out. And then the vertical kernel, same, just kind of on its side so that it's working in a horizontal direction, your GY. So all of the stuff kind of above the pixel is not given very much precedent, and all of the stuff kind of in front of it is. And so, the more change there is moving downward, the stronger the output of the kernel is going to be. And then the magnitude of the two images, which is our, should have forgot the word, IX and IY are the magnitude. And so you can just find the magnitude using your standard, xy squared plus xy squared square root. To save computational time, typically what will be done is just an approximation where you can see it's sort of absolute IX plus absolute IY. So that saves you from having to do squares and square roots, which isn't as big of a deal as it was, a while ago, because computers are pretty fast and already sort of optimized to do some of these things. But most of the algorithms you use out of the box, like an OpenCV, are going to typically use this sort of approximation. And so this is kind of how you break it down. The G sub X kernel, like I said, is change in pixel intensity from right to left while totally ignoring, the top and bottom rows of pixels. G sub Y cares about changes in magnitude from going from top to bottom while throwing out all the right to left stuff. And then we calculate the magnitude of the resulting IX and IY images just using regular vector addition. So we can also, of note, is find the direction of the gradient because we are treating it like vectors essentially. And that matters in better edge detectors. The Sobel operator doesn't really care, just a lot about direction of gradient. But once you get into more sophisticated edge detectors, that's something we'll kind of revisit and use. But essentially, what is happening is we kind of walk through this. So when I apply a high pass or a low pass filter or a Gaussian blur, I have my input image, I use my convolutional kernel, and I get an output image, right? So the Solver operator does that twice. So we get two images at the start of the Sobel operator. So when we start this type of edge detection, like I said, there's our two convolutional kernels, GX and GY. After we apply those, I'm left with my two intensity images, IX and IY. And then I calculate the magnitude of IX and IY to come up with my final image. That's my final sort of edge image. And then I apply a threshold to all of my pixels that now live inside this magnitude image. And any pixel, above the threshold is an edge, and any pixel below the threshold is not an edge. So, right, you apply GX to get IX, you apply GY to get IY, and then you can add them together using vector math, essentially, to come up with your final magnitude image. And then within that final image, you go in and throw stuff out based off the threshold or label stuff edge. So that's kind of all, like I said, all the other edge detectors are a riff on this, but the idea is, you could create one image that's all the vertical edges, and you create one image that's all the horizontal edges, and then you smash those together into one final image, and then you threshold that final image. So that's kind of the intermediary steps to keep in mind, is that you are doing edge detection on an image, and you get back the edges in that image. As you do so, you kind of create two intermediary images based off of the two kernels that you then put back together at the end after you do all the gradient calculation. And the reason this, direction is important is because better edge detectors will look at things like how to find kind of a shape, or find, if something's moving, these types of things. So that's a little bit for later, but we are going to work with it. But the main takeaway is, the reason we think of them as filters is because it works like a filter, because we're just sort of making two different filtered images and then mushing them together at the end. And so these are the outputs of just using the Sobel operator on, kind of our RIT mascot from before. One is with just these kernels. I can make it care more about bigger jumps by doing, like a -2, -4, -2 for GX zeros, and then 2, 4, 2, something like that. Or I can, change it to look for smaller jumps, but it's easier to kind of see this in a notebook. So right? You can see here for this piece, what we're doing is we're reading in that logo, and then I am giving it a X kernel for the Sobel operator, and you can see it's creating the Sobel image using my input image and a kernel size of 310. That means the 10 case size 3 basically is telling it to use this operator. And you can see that for both of them, except here in the Y direction, it's 0, 1, kernel size 3. And then to find the magnitude, like I said, we're just doing square root of the two things squared. And then I have to turn it into an integer at the end to create sort of the final image. And you can see now we're normalizing to make it easier to see. We're just sort of, we've got our magnitude, and we're just going to kind of put it between 0 and 255. So we can kind of see the black and white image, and then we're just going to plot it. So when we ran this, this is what we're left with. So we've got our original image that is brought in grayscale. And then here we're making our X image. So it's only looking at big changes from right to left. And so our letters all stand out pretty strong, and the outside of our tiger is pretty visible. We can see this over Y as we move down, the tops and bottoms of the letters and the middles jump out. The dark parts at the top of the tiger show up. A lot of the middle parts that we see in the X image don't show up as well. And then at the bottom, we've got our edges. And then the gradient magnitude, or the final edge detection, is just the magnitude of those two images combined, plotted in a black and white image. So we'll normalize 0 and 255 to get just our black and white edge image back. And so this is what we get just straight out of the box with those two kernels and the OpenCV detector. What we can do now is do this again for one of the iris pictures, and we can see, it's not great. We took the first thing we had, we didn't filter it, we threw our, sort of first algorithm at it, and we got back, something particularly, noisy and not super work withable, but it's our first pass at an edge detection. We've done edges in Y, edges in X, mush them together, blah, blah. Okay, so these are our two custom kernels. So you can see you just kind of like the notebooks before. If you want a custom kernel, you just make it with NumPy and define it as a custom kernel. And here, the X and Y, we can see we're using our custom X and our custom Y for this one, where now it gets way, way messier. And what that means is basically what's happening is when we raise the kernel, we're essentially raising how much it changes the magnitude as values change. So we're really overemphasizing jumps in intensity. And by really overemphasizing that, we're getting crappy edge detection, because like before with a high pass filter, we're telling it everything matters a lot by making the kernel so large that even small jumps of intensity get amplified by the larger kernel, so that smaller jumps in intensity look like bigger jumps in intensity when we look at the magnitude and the gradient. And so everybody kind of gets thrown in there as an edge. You can kind of see here, Up here, it's not great, but at least it looks like what it's supposed to look like. We can at least sort of still say what it is. Here, it looks terrible, but all the iris stuff looks terrible until we get much smarter in how we look at it. Here, with our custom kernel, we're basically saying every change is important, and we're making every little change look like a big change. And now, if I didn't already know I was looking at a tiger, I would probably not know that that was a tiger. And so it's just like edge detecting on a high pass filtered image, edge detecting with a really big kernel parameters like that for Sobel makes it pretty crappy. So conversely, we want to see what happens if we make it much smaller. So last time, this is essentially doubling the values in the kernel, and now we're halving the values. And you can see now it looks way, way better. And again, it's counterintuitive at first. Hopefully it isn't anymore at this point because we've talked the point to death and back. But when we blur things, when we weigh changes in intensity way lower, for us, it makes it harder to kind of tell what's happening. For a computer, it makes it much easier because on the one hand, here, I'm telling it every change in intensity matters a lot. All right, now here what I'm telling it is only really, really big changes in intensity matter. So raising a Sobel filter is sort of like applying a high pass filter. Lowering a Sobel kernel is sort of like applying a low pass filter, with the idea being we want to make the threshold as low as possible without throwing out too much stuff. But in other words, I want to weigh a change in intensity in a way that I only care about the biggest changes. And the way to only find the biggest jumps is to weight, everything as low as possible so that in a low pass filtered image, all of the sort of lines inside the face that are popping up all over, right? We're filtering out all of that stuff by only looking where there's, really big finite jumps. So there's our Sobel operator. And again, we can apply it just on an image. It sort of does the high pass or low pass filtering for us based on how we build the kernel. And, it helps us to know that if I am going to do the Sobel operator, if I want to just do a Sobel edge detector on an image that I haven't done anything to, I'm better off with smaller values in the convolutional kernels, GX and GY, because that will sort of implicitly do some low pass filtering for me. Conversely, if it's an image I know I would want to high pass filter before doing edge detection in a situation like that, then you can understand, well, then I'm going to make my GXGY kernels a little bit bigger. So it sort of filters and finds edges for you at the same time. And as long as you know how you want to be processing the image, if you kind of know to a certain extent it's going to need a high pass or a low pass, then you can make custom kernels for the Sobel edge detector and use it. Of course, all this to say, you're not going to use a Sobel operator very much because it is sort of the base case. I don't guess you guys have Dollar General. I don't know what the equivalent is, but right, there's like Kroger brand, and then there's Great Value brand at Walmart. And then if you kind of move far enough down the ladder of grocery stores, you get to Dollar General and Family Dollar, where they sell Clover Valley brand foodstuffs that are rough approximations of actual food. So Sobel operator is sort of like your, best choice Clover Valley brand Mr. Pibb of edge detectors, I guess, whatever generic knockoff you want to think of. So we know we can do better. Surely there's a way to do better, right? We know enough about images and we know enough about algebra, magnitudes, and gradients, right? So kind of our next step up in smartness ladder and the one you guys use for assignment one to just kind of do some straight up edge detection in terms of, have different color spaces giving you better results without needing to know how the Canny edge detector worked. Now we're going to kind of cover what is going on under the hood, what makes the Canny edge detector work. And it's just a Sobel operator, but with filtering. So for the Canny edge detector, it applies a low pass filter before applying the GXGY kernels. And that's one of the extra steps, with the next steps being there's non-maximal suppression and hysteresis. So it's a Sobel operator with some pre-processing and some post-processing, essentially. The first thing it does is do a low pass filter like we were kind of doing ourselves before. And then we saw if we wanted to get a high pass or low pass filter effect with a Sobel operator, we have to change the kernels. In a Canny edge detector, the goal is you don't have to touch the kernels for Sobel for GXGY because you make a first pass filtering and then you do NMS and hysteresis post-processing. So it's a Sobel operator with some pre and post-processing. We already know how a low-pass filter works, or Gaussian blur. We've covered those. We know how to do that. We just, again, we give it some sort of kernel, apply it, filter it, and come back with our filtered image. And then we do our GXGY, IXIY, calculate the magnitude. So what are the extra post-processing steps? There are two, like I said, so there's non-maximal suppression. What that is used for is, I'm just not sure if it's for this class or something else. All right, that's not for us. All right, so I will ignore that. And yeah, so non-maximal suppression is used to thin the edges. So when we look over here, even with our good custom operator that acted like a low pass filter, I still have very thick edges. And you can really see that in, around the muzzle and these areas, you still have all these little bitty noisy edges that kind of show up anyway, or you can see there's a lot of like wigglies throughout the letter edges. It kind of puts everything that's edge-ish into the edge. There's no sort of not necessarily smoothing, really thinning, right? The idea is if we look in the image itself, theoretically each edge is only 1 pixel because it goes from white to R or white to a tiger. So the most pronounced edges are only a pixel, and then if you kind of expand that and allow an edge to kind of be more and more pixels, then you get these wide edges like we see. So what we want to do after we get these edges on our custom gradient here, right, after we get those, before we actually return our edges, what we're going to do is thin them. And what that is it basically looks at everything that has been labeled an edge, and then it filters out anything that is not a local maximum. Basically, what it does is you have, all of your pixels that count as edges. And what NMS does is it looks at all of them And within, sort of each piece of edge, it only keeps the local maximum. So if we kind of look over here, in here in particular, kind of on the outside of the tiger, you can see there are lots of holes in the edge, right? You've got this white edge, but there's still a lot of black spots in it, and so what NMS does is it essentially gets rid of all of those and only keeps within each edge the ones that are much higher than everyone around them. So it's kind of, the trailing sides when you find the edge and when you leave the edge, just sort of get weeded out if they aren't bright enough or intense enough relative to everyone else that's part of that edge. And then what hysteresis does is it connects the edges. So hysteresis is sort of based on the idea that an edge should be continuous or it should be at least a certain size. So what hysteresis does is it bends basically all of the weak edges and all of the strong edges. And so it looks at, the thick edges, they're, big jumps in intensity, kind of the weak ones are where there's little jumps in energy or they're thinned out to be really small after NMS. And it says, okay, if it's a weak edge that touches a strong edge, that now becomes one edge. So it's essentially connecting any weak edges that touch strong edges into one edge. And weak edges that are not connected to a strong edge are suppressed or they're thrown out. So again, kind of if we look here, you have all these little bitty edges inside the face and the muzzle where it's a little bit of whiskers or it's a little black spot or something like that. So all these, kind of see-through black and white patterned stuff, what the canny edge detector does in the hysteresis step is, for every little edge we've picked out, if it isn't touching a bigger, stronger edge, it just gets thrown away. If you look over here, if we go back to our iris, right, over here, we have tons and tons and tons of these little weak edges that look like noise. They almost look like static, right? That's effect is just basically a ton of really tiny weak edges. And so the goal with the canny edge detector is to, all of the staticky looking bits that are the really weak edges just get thrown out. So the canny edge detector, so we got here. All right, so the canny edge detector is just a Sobel operator with pre and post processing, and Sobel operator is just a high pass and low pass filter in two directions. So it all kind of builds off the same concept of, I'm applying some sort of filter that's some function of a high pass or a low pass, and then I'm applying it in fancy ways with, kind of the GXTY, and then I'm post processing it in fancy ways, but at the end of the day, it's all just sort of an amalgamation of different versions of filtering with convolutional kernels. And so here, what we're doing is we're just with the high and low thresholds that come with the canny edge detector, 100, 200, we're just going to apply that to our tiger. And now there is a straight line for each edge in the image that is clearly an edge, right? And so now we've kind of gone from, initially we were trying to find edges and we got, this terrible thing, or if we look at the iris, we get this even more terrible thing. If we're clever with how we define our kernels, we can get something slightly less terrible. Or I can just kind of cut out the middleman of all of this and use the canny edge detector, which does the filtering for me and then goes in and suppresses everything that isn't a very strong edge. So what we can do next, if we want to see a little bit more of how this works and how this affects things, we can change the threshold. So here we're doing 100, 200. If we drop this way down to 10 and 20, what does it look like? Or if I do 180, 190, or 0, 10. So this is just three different thresholding. So if we keep everything that is, if we do 10, 20, we're sort of keeping everything. If we're doing 180, 190, we're keeping a very narrow band of things. And if I'm doing 0 to 10, then I'm keeping everything. So what is basically happening is as you lower the threshold, right, here kind of our lower bound is 10, here our lower bound is 0. The more we lower that, the more weak edges it keeps, right? So the more stuff shows up in the image ultimately. And you can see kind of from this, the bottom threshold, kind of the lower end of how low it can be for you to still keep it. Lowering that makes things worse way faster than raising the top threshold will change anything. Because if it's kind of at the top, if we're thinking of, a 0 to a 255 value, if it's already over, when we look here, if it's already over 100, right, out of our threshold, then it's going to show up as an edge anyway. Same as if it's, being over 100 and being over 180, there's not a huge change, I guess is what I'm trying to say. A strong edge is strong enough that you can raise the top threshold high and still get what you want and usually get a very better solution. But the more you lower the threshold, the more stuff you keep, the worse and worse it's going to get. So you got to kind of figure out as you're working through things where that threshold needs to be for your application. And just kind of the general heuristic, like a good rule of thumb, is a higher threshold is thinner, cleaner edges. And this last bit is like we were doing with the color space stuff. We know that a canny edge detector is a pre and post processed Sobel filter. So just like we can kind of by hand create our hue saturation spaces, VLI, we can just by using the Sobel operator that we get from OpenCV, we can create a canny edge detector basically from scratch, which is what this is. And this is the type of thing that will be on the next assignment is, creating your own edge detector from scratch based off of convolutional kernels in the Sobel operator. But what this does is we go in and the first thing we do is create the blurred image, which is Gaussian blur, which is just a name for low pass filtering. That's the name you usually see it given because it works off of Gaussians. So it's called Gaussian blur. Just know that that's really just a low pass filter. And then we've created our Sobel operators. So these are the two that it normally comes with, or 1, 2, 1. So we use our filter 2D on the blurred image with these two kernels to get our gradient. We calculate the magnitude of our gradient based off of those filters. We calculate the direction and see arctangent. So through here is we've just done a Sobel operator, then a filtered image. The fancy candy edge detection stuff starts here with the non-maximal suppression. So the first thing we do is we create our suppressed image. It's just full of zeros to start with. And then we get our direction. So which direction the edge is sort of moving. And through here, we've got this loop that does the non-maximal suppression for us, where it is seeing if each sort of point in the filtered image is a local maxima or local minimum. And you can see basically at the end, if it is above some magnitude and yeah, so if we're above our direction, sorry, if we are above our suppressed magnitude, basically if we're above whatever we're telling it the cutoff is to suppress local minimums, then we throw it out. And if it isn't, we keep it. And so the next thing we do is our hysteresis, which is essentially a double thresholding, where we say a strong edge is something with this value, a weak edge is something with this value, and these are our thresholds. So we find our strong edges everywhere inside our NMS image that is above the high threshold. And we find all our weak edges where they are below our threshold. Mush all that stuff back together into our final image. And here you can see we just sort of mush everything together based off of all the thresholds we've given it, and it gives us back our image. And so we wrote our image out, we wrote everything out by hand. And it works kind of, I mean, good job us for writing out a ton of math we didn't necessarily need to write out. If anyone can drop in the chat or figure out why it's not as good as the OpenCV option, some more bonus points available. Because, we've done all the math more or less how the math is supposed to go. We have our filtering, we have our gradients, we have our NMS, we've got our double threshold for our hysteresis, we find our edges, and we still kind of miss some stuff. And if anyone can go in and figure out why it missed some stuff when we wrote it out by hand, you can have some bonus points. So that gets us through the Canny edge detector. And now we're going to look at some more advanced options. So most of what you'll see done is going to use a Canny edge detector just because yes, the version we wrote out does not do a good job attaching weak and strong edges. So congrats. Yeah. What OpenCV does for us during this part that we didn't do with our math is connect strong and weak edges as well. And that's why we have lots of these little disjointed edges here in our version. Whereas when we look at OpenCV's version, we don't have a lot of these little bitty edges. We don't have lots of disconnects. So matching weak edges to strong edges is harder than it sounds like. And there's lots of different ways to try and threshold it. And we just kind of did this like, well, if they're kind of touching, we'll kind of keep them, and there's some real hard limits in terms of, what counts as connecting that OpenCV is much better at doing for us by doing a, much more advanced hysteresis than just, 3 if-else statements. So dope. Very nice. So that gets us through, sort of how we detect edges out of the box. Kind of like with the OpenCV conversions library, where you can convert from any color space to any color space a million times over. There are a ton of edge detection operators, there are tons of options, there's tons of thresholding. We're going to talk about two more edge detectors because they operate, a little differently than a Canny edge detection. So we'll cover these, and like I said, going forward, everything is kind of a riff on one of these three options: the Canny, a log, or a Schur operator. So the Laplacian of Gaussian or log. So the Gaussian is the change in intensity, which is the gradient. The Laplacian is the second derivative, which is the change in the change of intensities, basically. With our Canny edge detector, we are looking at jumps in intensity. With a log edge detector, a log filter, we're looking in jumps in intensity. So it's just the second derivative of what we are doing with a Gaussian filter and a Canny edge detector. So conceptually, that's all I really need to think of it as. And mathematically, the Laplacian is defined as this big nasty thing that we aren't necessarily going to want to do to find our edges. So the way we kind of actually apply it to get around, partial differential equations, which computers struggle with, what we can do is, instead of measuring changes in intensity, it measures changes in intensity, like I said. And what this does is it flags pixels for changes in any direction. So that's what's nice about the log filter, is it is not fixed to doing vertical and horizontal sort of separately. It's a little more direction agnostic. And so what it does is looks for zero crossings. So areas where it goes from positive to negative or negative to positive. So before, where we're looking at a jump in intensity within some threshold, now we are looking for a zero crossing in the Laplacian, where we're going from positive changes in intensity to negative changes in intensity, right? And so by looking at the second derivative and this idea of zero crossings, we're essentially just seeing where the sign of the gradient changes, which means we either went from very low intensity to very high intensity, or very high intensity to very low intensity, without necessarily caring about the things in between. So you can think of, if we look at our images, right, we have some thickness to our edges, like I, kind of going back to where we are trying to do NMS to thin the edges because, there's several pixels within the edge. By looking at zero crossings, it's another way to try and thin an edge to where we really only care about, right, the exact pixels where it goes from not edge to edge and edge back to not edge. So by using zero crossings like this, by using the Laplacian, Gaussian, or the log, it really helps out with noisy images, because it's sort of like NMS times a million, right? It's more of a thinning factor than even just an NMS or hysteresis. So it's good for noisy images because it cuts out on a lot of the stuff that's teeny edges. It's better than hysteresis, or where you're connecting weak and strong edges. In this case, it just doesn't find the weak edges to begin with because of how it operates. But again, it's partial derivatives, then it's second partial derivatives, which because we've talked about this, and especially with images where pixels are discrete values, computers just can't think or display continuous data, especially images where every pixel is discrete. And that ultimately kind of boils down to computers suck at solving partial differential equations. Um, we can approximate them lots of different ways. All of them are still pretty slow because, again, computers suck with working at things that are continuous, like integrals and derivatives. So computationally, it costs us a lot to use a log filter for edge detection. Um, Depending on the application, that doesn't matter all that much, right? If you are working with data you don't need to process in real time, or if you are working with images that are very, very complicated or very noisy, and you know you want to do a lot of different kinds of post-processing, it's good because it's a very good edge detector. Um, but when you think about things like 3D video processing or any sort of real-time image processing, um, you kind of can't use it or as much as you want or as often as you want because it does cost a lot to run. Um, so the benefits of it, like I said, it captures changes in multiple directions. So by computing the Laplacian, we're bypassing the convolutional kernel step where we have to filter out vertical and horizontal edges separately. Instead, this will just capture changes in every direction. And by looking at zero crossings, it can detect very rapid changes, so it can find thinner edges depending on how you're using it. And the nice thing about it is that it also can do the Gaussian blurring while running the operator. So we don't have to kind of do that step of low pass filter, then edge detect. We can just directly apply the log. So it basically just does a blurring and Laplacian calculation and then goes in and finds zero crossings. So this is our handwritten Canny edge detector. So here we're using the log filter. So again, we're blurring it. So we're making our low pass filtered image. It's a little blurrier. And then on my filtered image, I just drop in my Laplacian. And I say, hey, OpenCV, use a Laplacian because no one's going to calculate this by hand. And then, you can do some conversion to make it a little easier to look at. And if we run this code, we see the results of the log filter. So what is different with this image is that we now have separated the leading edge and trailing edge, right? You can see everything is now outlined. There's an edge, nothing, and then an edge. So we've got like two edges around every sort of edge we got in the Canny edge detector. And that is because it is looking for zero crossings. So when it gets to the left side of the R, right, it sees an edge where the R starts, and then it sees an edge where it becomes just solid black inside of the R. And so that is what is happening, is there's a zero crossing when the R starts, and then some distance into the R, you have another zero crossing where it stops changing, it just becomes solid black. And so it sees when it first becomes solid black, and then it detects another edge where it essentially has run out of white pixels to the left to determine an edge, so it's not changing anymore. So now that it's become solid enough black, it stops seeing the edge. And so when you use a log filter, it's very, very common to see two edges like this. You know, if you are working with big geometric shapes like these letters in this face. And again, that is an effect of the zero crossing, where it crosses zero when the R starts and it crosses zero again at some point when the R becomes nothing but solid black. And so we want to kind of see, well, how well does this work in a noisy image? It doesn't look just a whole lot better than any of the stuff we've already tried for this iris image, though we do definitely see every edge is now kind of two edges, right? There's a where the edge starts and where the edge stops, basically. So our log filter did okay, right? If we come up here and look all the way back up here and our iris, you know, that looks pretty bad. If we come all the way back down here, it looks a little bit less bad. It's a lot less noisy and it's still got some edges, but it's still not really giving us what I want. There's no real like flower popping out at us. So the last one we'll mention is the Char operator, and this one is based off a Sobel operator. It's just a version of it that is meant to find angles, so 45-degree lines. So if you think to the Sobel operator, it's finding vertical edges and it's finding horizontal edges, but it's not finding any kind of curve or angle or line that isn't essentially at 90 degrees or 0 degrees or 180 degrees. At 90 degrees, it's not great at finding those. And so a kind of a subset of that is the Char operator, which has kernels that are designed to look for angled lines. And so we can, we do the Char operator. It's in OpenCV. We're essentially just saying, hey, apply a Sobel operator with this GXGY kernels to look for edges that are on a angle, like a 45-degree plane. So the edges, if we kind of look at it from 45 degrees all the way through, we kind of get this output now from the Char operator. So obviously none of these look good, right? So we can't just kind of pick something up and run it straight away and know we're going to get good results, because the Char operator is looking for angled edges, which are a little harder to find. We've got our log filter, which is looking for zero crossings. We've got our canny edge detector, which is looking at straight lines and then attaching them to each other, suppressing some edges, doing some thresholding. The main takeaway between all of these is that the log filter finds curved edges the best of all of the options. The canny edge detector is the best at lots of straight lines. So you can see we've got lots of straight lines. You can see the one we wrote by hand doesn't have any curves in it because of our inability to connect edges. It doesn't really see curves because it doesn't connect an edge that's a little bit above this one. If there's a little gap, it's not going to connect those to turn into a curve. It's just going to give us back all these straight lines. Because the log filter works in all directions at the same time and only cares about a zero crossing, it finds all of these curves for us. And you can kind of see we have a lot more curved edges in our log output. And then the Char operator, it has fairly limited utility unless you're looking for things that are at an angle. And so you can see all of the things that are sort of at 45 degrees through here show up, but the rest is just a lot of angry noise. And this is just kind of the last thing for today because we're kind of out of time. But, this is the edge detection operators we've kind of covered and how they work. So there's the Sobel, which is sort of the starting point, like it's the starting point for the Canny edge detector. Like I said, it's, that's kind of the workhorse of edge detectors. It's what you use most of the time. It's good for nice, clean images, like we showed, the classroom with the desks, it works really well. The irises, it does not work very well, right? But it's kind of just your workhorse out of the box. I'm going to start with Canny. So the log filter is kind of the best. It's good for noisy images. It's good for finding curves. So it's really good for segmentation. It's what gets used a lot in a lot of classification tasks, with kind of the caveat being you will get 2 lines for every edge, depending on how it is looking for zero crossings. So you have to be aware of that, and you have to be aware of how to threshold it so that you don't end up with double edges like that when you don't want them. And then the SHAR operator is really just for some niche applications to show that you can build a kernel that will look for angled lines in addition to sort of a Canny and Sobel, which are looking for vertical and horizontal. And then, kind of the overall statement about edge detection before we move on is just that usually you'll apply some sort of ensemble, or you will apply some sort of custom kernel, with the idea being what your application is. You're going to want to find edges with some sort of properties, and it's going to kind of be on you to find the edge detector and kernel and filters that get you where you need to go. So other than a lot of applications that just straight up call Canny 2D, most of the time you're going to kind of need to know enough about how each of these work to sort of build your own. And then some stuff, I've just put a couple cool videos up there that are real sort of simple. And then a paper that talks about how you use ensemble models to segment and detect edges. And it's got some cool stuff in there about optimization that we'll get into a little later in the semester, because CV is usually pretty computationally intensive. And in addition to knowing how things work and what we want, there's also a lot of onus on us to know how to make them run in a reasonable time scale. So that's going to be it for today. I'll push this notebook to the repo for everybody. See, I'm just going to mark who got the bonus so that I'll know that. Yeah, just save this. Okay. So awesome. Like I said, everybody get your stuff in today by the end of today. If you're not going to get it in today, tell me, we can work something out. And otherwise, I will see everyone Friday, and we move on from edge detection and filters to some more applied stuff. So awesome. Have a great Tuesday, and I'll see everyone Thursday. Bye all.